Today for this session, we have three experts, including Joseph, Udayan, and Chad. So instead of I read out the long list of achievements of you two, maybe you two can first give us a brief introduction yourself.
Yeah, sure. I can begin. I'm Chad Sweet. I'm CEO at Modal AI, which we spun out of Qualcomm in 2018. We work primarily on building computing platforms for drones and robots. And of course, the computing platforms need to communicate. And they all, today's drones and robots perform an incredible amount of edge computing, AI, SLAM or simultaneous location and mapping, flight control, of course, keeping the drone in the air. And so happy to join the panel, and thank you for having me talking about edge computing as it relates to communications.
Thank you, Chad.
Good afternoon. I'm Udayan. I'm Intel Senior Fellow. So I lead the silicon and system design for wireless, which includes 5G radio access network, packet core, and the edge computing aspects of it.
Thanks. I already introduced Joseph. Do you have anything to add about yourself? No? Okay, so we'll go with this format for this panel. I prepared a few very broad questions just as food for thoughts. And if the audience have additional questions, feel free to come up and to the mic and speak up. So my first question for the panelists is, there has been a lot of discussions about edge computing and edge communications, and we see the word edge everywhere right now. And so right now, what do you see are the key applications or use cases of edge computing? And this include, of course, both the commercial use cases, but it could also be for like use cases for academic research. And use cases not only in communication, but maybe also in computing and even some very application-specific domains like health and so
on. I can start.
Go ahead.
So there are multiple dimensions to this edge computing aspects of it. Obviously, if you look at the wireless network, the radio access network RAN, or the cloud RAN or virtual RAN, even though it's called cloud, those are all getting deployed at the edge or far edge of it. So there are a massive amount of compute aspects of it, and there are a lot of AI elements getting into it. For example, how do you do channel estimations? A previous speaker talked about, in the panel, talked about beam management, beam weight generations. Those are all aspects of the compute that is happening at that edge itself. But there is another dimension to this. A lot of these networks are now getting built in the private network context. Companies like Siemens of the world and Audis of the world are building 5G networks to link it up. So there are a lot of data being generated in that premise itself. That elements of that needs to be, there are a lot of compute aspects of this getting into that edge. So there are multiple those use cases coming from the network side of it. And once you generate the data, what do you do with the data? So those are the dimensions.
We see the word data again here, right? So how about Joseph and Chad?
Yeah, add on that. So, before going into what is the compute that's happening at the edge, it's fascinating to see what's happening with generative AI in terms of in this last few, let's say, half year or so, real big move towards multimodal, and it's a lot of what we've been seeing before is a lot of text and very interpretable to us, but as you see going forward. The tokenization of these different modalities really opens up what you're able to do with things. And then we start looking just even at a design standpoint of what the machine learning autoaggressive transformer model can do if you map these different modalities into the same kind of linear latent space of these other representations. Right now you see video, you see speech, you see text. You can also put in radio. You can put in general audio, not just speech audio, and it's fascinating that the level at which all of this is happening. Now, when we look at these applications, and some of these are even decision based, like a token itself can represent an action that you take. When we look at what's involved for the computing that needs to be done, my big question is is that the same computer that I have at the edge, or do I have to change it? And that's a lot of what we're going through right now, is seeing how much of that can we map, how much of our edge computing technology has to evolve from where it is now to be able to really realize the ubiquity of these things happening. And unfortunately, I wasn't able to share this with you, but there's a lot of really encouraging movement in this direction. That I know a lot of how we're investing in silicon, in evolving what the compute paradigm is, from going from like a CPU to a GPU to NPU. All of that is in a very good direction for us to think about the compute everywhere can be able to handle some aspect of generative AI. And then we can look at, okay, how can we distribute it? How can we take advantage of it and interlink it with all these other things that have computing on them?
Yeah, so this generative AI just emerged very recently, but it's quickly becoming a kind of killer application of edge computing.
Yeah.
Right? Yeah. Chad, do you have any thoughts about this?
Yeah, I could just, comment on the broad applications. I think what's driving the advancement of edge computer, autonomous driving, autonomous navigation in general, robotic autonomous navigation, and certain rendering, virtual reality, and so forth. The digital twin folks preceded this, and I think that's obviously going to drive a lot, or is driving a lot of the advancements in compute at the edge. And of course, AI and generative AI are a big part of that. I think that's going to be pervasive in all of those technologies or all of those applications.
Actually, just to add to that, generative AI is going to be huge. I mean, you have a startup company like Iris and others have actually talked about this. RAN GPTs of the world, they're building, that bringing the data from radio access network, packet core, and others, and they're making, a lot of prediction. But that's not the only thing. I mean, there are a lot of models being used. I mean, even simple models like MLPs or even linear regressions, to select dynamic power management aspects of it in the infrastructure layer. So some of the layer 1, layer 2 aspects of pairing of the users or emulating or finding out the weights for the channels. A lot of simpler models also can be used and which are being looked at. So there are AI, ML, if you talk about it, every aspects of it.
Right.
So.
Yeah, this actually also leads to my second broad question. That is, what is your perspective on the synergy between AI and edge? I guess broadly we can look at it from two perspectives. One is AI for edge, the other is edge for AI. So AI could be the powerhouse to somehow enhance the edge performance in both computing and communication. But on the other hand, the edge itself can also provide the computing power and also the communication facility to enable distributed AI, right? So what do you see as the potential of this synergy? And are there any other ways of looking at this?
So I think to talk about the second point is if AI is moving to the edge, I think it's really just broadly the natural progression of Moore's law in computing, where you start with big racks and you end up with tiny little devices. And so I think the closer you get to the edge, the more applications open up, right? The more you can have in your pocket, the more you can have on you or near you or around you, the number of applications expands, right along with it.
Yeah, go ahead.
Yeah, a couple of interesting things you can say about just AI coming to the edge. Of course, Moore's law is a big push for that. One interesting thing that I would say that a lot of edge players are benefiting from is that once, let's say, like a large cloud model shows its proficiency, there is also a lot of pressure to make that very efficient. Because if it does become a service that is very popular and wants to scale to, say, like 1 billion users, even the cloud will want something that's small and efficient. And then just by nature, it comes to the edge because it's already been trained really well, it's been focused for the domain that it's in. And then you kind of all benefit from that ubiquity. Now, there are things that are going to be very unique that bringing it to the edge. entails. I think some of the things that there's the genuine, you may not be connected to the cloud. There's privacy. There's these aspects that are very, very, they're old topics that we come back to for just the point of having compute at the edge in the first place. But when it comes to more of AI interaction, there's a lot of kind of situated awareness that it's not necessarily clear you can scale that up to every single entity or user or and so forth. And by being able to move a lot of that compute and a lot of that perception at the edge, then some of that real-time interaction can be more ubiquitous, be more useful. It doesn't have to be like a broad AGI type of experience. It can actually be very applicable even in a very narrow domain. But that's one like unique point about all the effort in bringing things to the edge that we see coming.
Just to add to that, Moore's law is a good way of thinking about it, but there are some real use cases that is forcing AI to get in the edge, data governance, data ownership. I've had operators telling me they don't even want to see the prompts going out of that network. So prompting, you talk about, using public LLMs of the world. So a lot of those, intellectual property ownership and stuff is happening there. And the data, the compute, whether it's an AI or any elements of compute will go where the data is. And the data are being generated at the edge. Right. So even though all the generative AI stuff started so much in the data center cloud, which is the right place, and there's a lot of innovations are happening, but you will see next few years most of those things are going to be distributed and at the edge. And edge may very well be at the far edge. It can be AI PC that Qualcomm's, Intels of the world are working on. It can be it will be in the phones. So there are all aspects of it.
You mentioned privacy. Is that different? Is AI privacy different? I mean that purely out of curiosity. I have no idea.
Data ownership and data governance is, I don't know about the privacy part of it, whether it's different. Privacy is key. But what the operators are telling me that I need to keep all my data in my premise, on my premise, which is basically at the edge, at the far edge. If you look into what Verizons of the world do, what AT&Ts of the world do, what Vodafones of the world, they are having those data. So it's not basically, even if I use a public LLM to do few things, there are even that the prompt engineering aspects of it. The prompts also should not even go.
Yeah, I guess is it different than your Google query?
Exactly.
Yeah, I don't know. Okay.
You all talked about AI coming to the edge. So is there a case for using AI models to enhance edge performance? For example, enhancing the communication efficiency, computing efficiency, energy efficiency, and so on?
I have a favorite one.
Go ahead.
That I don't know how to solve, but if anybody does, happy to talk about it. But I think real-time video in use cases where accuracy isn't quite required, but so I think of like flying a drone or remotely piloting some sort of robot. I don't know about a car, maybe a car it applies to, where you could send highly compressed video or even something even more basic, more fundamental, describing the scene or describing the deltas of the scene with a very low bit rate and then rendering it in full resolution at the operator. And so, with the goal of, really surviving interrupted comms links or non-robust comms links with a lot lower bit rate. Instead of, say, sending 4K video, could you actually send a much lower resolution, but give the operator the impression that they're operating with really high fidelity data? Right. You think about like avoiding a tree with a drone. Well, you just need to know that the tree's there. You don't maybe care about the nuances of the leaves. You could fake the leaves with AI or generative AI, and you can still fly safely.
That's right. Yeah, this also reminds me of the concept of semantic communication, which emerged recently. Instead of sending a picture per se, you can just send a prompt and the receiver can recover the image by themselves.
Exactly.
Right?
Recreate.
Exactly.
This is
Now
one-
do it in real time.
Right. That's another challenge, I guess.
I can tell you what is happening today. I mean, we are deploying a lot of virtual RAN elements of in operators network. There are two aspects that AI is really getting into it. One is the infrastructure side of it. Dynamically, you do the power management based on the load line. So, the power that you're drawing from your wall essentially includes of CPU power, fans, everything else. How do you actually dynamically control this, predict this thing? So there are a lot of AI technologies getting into it, and we are deploying some of these things in the virtual RAN in FlexRAN-based systems. So that's one aspect of it happening. The other aspects is coming from the deployment, day 0, day 1, day 2, deployment, automation, and troubleshooting side of it. There's a lot of startup companies like IRAS of the world, few others, they are actually developing the LLMs of the world to actually put the logs and files to actually help them do these things. These are the two aspects that I'm seeing right now happening. The next one is coming, which is also 3GPP looking to beyond 5G as you get to 6G side of it. So how do you potentially not replace, but actually enhance the layer 1, some of the classical algorithms that we know and grew in from 3G, 4G, and then 5G? Can I add some selective AI elements to actually improve the KPIs? Whether I can do better, the users at the edge, better RB selections, MCS selections, dynamically varying some of those aspects of it, not just fixed, not static way. So that's the next level of stuff. 3GPP standards are also looking into some of this. We are also looking into.
Right. I think
Yeah.
quite a few companies like NVIDIA are already
Yep.
investing into this direction. Right?
Exactly.
Yeah, if we could add one more. One more thing about so AI improving, let's say, communication or compute or things that are related to that aspect of the edge. It is like let's say like a long-standing thing that we're always trying to do some kind of prediction, and it gets better with data-driven. Maybe several years ago there was small models to figure out branch prediction in a processor, for instance, and then we go and see, now that we have more powerful models, what more can we do? One thing I see that is still like maybe more of an open research topic is that it's more obvious when you look at what's happening in, let's say, vision and perception, that some of these massively foundational pre-trained models, they have a great, let's say, like generalization or open set capability, where you don't necessarily have to have every example anymore in your data set, and you just have to have enough fine tuning on this pre-trained corpus, and suddenly it can do very well in these new domains. And that's something that people are still trying to let's say master, even in the state of like auto perception, for instance, or robotic perception. But it is quite an amazing capability that is coming together. And then we're putting it together with language and vision models, and even in domains that are not language or vision, but the idea that you may see a lot of code programming tools that are auto completion or analysis of code. Some of that is on a pre-trained corpus that may not have anything to do with code. And it's interesting that sometimes that's actually a good starting point for some of these things that they use. Just similarly for these image generation models that you may see, they have a perceptual capability implicit in them that people are understanding to use for image restoration and so forth. And they're trained on a corpus of not necessarily perfect images, but just the fact that it has a corpus of everything that can possibly be seen is, raises an interesting research question as to what should a diverse data set be like, and how should you build upon that. Going outside of these modalities that are very natural for us to understand, and going into, say, wireless or optimization or compute, those are, I think, new challenges ahead of us. And I've seen some really interesting progress people have made in that, but I think there's still a lot ahead of us there.
Right. This is actually also leading to the third question. I want to ask, from your perspective, what are the remaining challenges, technical challenges to solve towards the vision of intelligent edge? So these challenges could be short-term challenges, could be long-term challenges. And some of these challenges could lead to a research paper for our students or even a PhD thesis, right? So it will be good if you can share with us some of your problems and some of the challenges in your mind.
Edge in general is quite power and form factor constrained environment. It's not the massive amount of expensive GPU clusters you can put in some of the far edge and edge elements of it. But the requirements, many of the requirements are similar. I'm telling you, in a wireless side of it, like as we move towards 6G and AI native and all of it, we are also struggling, and this may be somewhere, that traditional algorithms, baseline aspects of it, like MMSCs, the MLDs, and channel estimations, are doing very well. I mean, so forcing AI there and seeing that if there's anything, benefit or not, I mean, is one to look into. But getting what do you do? AI. I want to inject that in the layer one. Am I getting any benefit in the KPI side of it? Still, our Intel lab, I know that we are funding that. Find out what can I gain, whether in terms of spectrum utilizations, whether in terms of lowering the complexity of the processing. So there are a lot of those challenges that we are facing at this point to see where we can actually inject it, and so that maybe more wireless, fundamental wireless resistors required. But some of these algorithms are very much well tuned.
That's right.
For years.
Yeah, at least for wireless communication, we have the ceiling bound and the channel ceiling bound there.
Exactly.
We're very close to that bound, and it's unclear what else we can do, right?
Exactly.
Yeah, but potentially, there could be other ways of thinking about communication, like going back to the concept of semantic communication.
Yeah.
Do we really need to send information in the form of bits, or can we just send information in the form of knowledge, facilitated by the edge intelligence somehow, right?
Yeah.
Maybe that's a way to sidestep the channel bound, I guess.
But you had to go back on, say, video, but we'll make it video telephony. You could imagine the first 5 minutes of your Zoom session, there's some generative network training on people's faces and voices and so forth, and then taking that information and conveying it semantically from then on, or periodically, or to keyframes and p-frames. You could imagine just filling in the gaps with generative AI. Of course, you have to achieve that real time, but that I would imagine would radically reduce the overall bandwidth required to send video and hold a video conference. And everybody still struggles today with, it's breaking up. You're breaking up. Can you shut off your camera? Can you, send a lot less data. You're training. You have all the content there. Train it first in the first few minutes.
Right. So related to this, I think you already alluded to this. One challenge is the real-time challenge, right? So in the future, suppose we want to run this kind of intelligent edge, a lot of the processing has to be done in real time. So what do you think is the fundamental challenge there? Is it just about computing, or are there any other challenges we do not straightforwardly see?
As Joseph was alluding, but there's a lot of optimization left.
Yeah.
You see this stuff deployed on a server first because obviously the work is not easy, but it's straightforward to deploy when you have unlimited computing resources. That's the first crack at it. But generally those models and designs and implementations are not optimal in any way. They just got it working. Then you got to optimize. And there's usually a few passes that can occur just in plain software optimization really quick right up front. And I don't think that'll get you to real time on your phone today, but then you pull in the computing and the two meld together.
And optimizations in terms of both software, as probably you are alluding to, and also silicon. We are enhancing the silicon to actually do a lot of real-time aspects of it. Even think of, 10 years back, who thought of running layer one on a general purpose processing? It was the domain of custom ASICs and stuff. It's still they're dominant, but there's a lot of those movements that with the virtual RAN is happening. Those layer one TTIs are real-time processing. So a lot of enhancement in the silicon has happened. So I think a lot of optimization, as you correctly said, optimization left.
Yeah, there's some interesting things that I completely agree with my colleagues. There's some interesting other things too, just in the space of machine learning, when you come to real time situated. So if you think about voice UI that's there today, a lot of it is question answer, kind of very polite, and the natural state of things is we're interrupting each other all the time, and in reality, you have to kind of train a network to do that. You have to have a corpus that has a lot of interruption, has the polite way to respond to an interruption, the proper way to understand how to pivot your train of thought in light of an interruption. These kinds of things, affect the machine learning level, and then they propagate themselves to how do I deal with an interruption at the software level when I built my system for a very regular Q&A kind of flow. One thing I wanted to talk about on the challenge side from your previous question, kind of speaking to some of the researchers and students here too, is there's all sorts of challenges, as you say, near term, long term. Compute and data, I think, are always like a really restrictive challenge, especially even silicon companies are not like cloud companies in terms of what training infrastructure is available. It can be a challenge to the academic community as well, I understand. There are different ways that should be addressed, but that's something that shouldn't be taken lightly. Hopefully there's some ways that investments can go in that direction. At the same time, there's a lot of very interesting ways that people are innovating in the other direction. So last year we had a slew of very large language models, for instance, coming out open source from Meta, from some other examples from like Mistral in Europe and so forth. And then this year, if you follow, a lot of models now are smaller than they were last year, and they're better than they were last year. And
That's right.
if you look a little more closely, they're training faster, and in some cases, they use a larger model to synthesize data and get it to train much more efficiently and be more proficient. So there are clever techniques that help us to get around the data problem, help us to get around the compute problem, and then reuse a lot of amortize the investment we did in the previous generations to build new things. And that's only in the space of language. Who knows when you go to these other modalities that are more relevant to what people work on here, if you can play the same game and benefit generation after generation.
It's just surprising how fast this field is evolving. And I want to bring back another question about security, right, which is very important for edge computing and also is one of the motivations behind edge computing. So with the edge servers, we still are not completely solving the security problem, right? Because we still have to offload the data. So do you think if there is an absolute solution to this, should we just localize our data to our smartphones, or is there any other better way of doing so to ensuring security? Any thoughts to share?
I can start.
Go for it. Yeah.
Yeah, I mean, I think it's understood among a lot of folks that there's levels at which you can make things secure and confidential, and I think because we're so far into cloud services, people have also become somewhat comfortable with the fact that it's going to be protected in the cloud. And then there are going to be some levels at which they have to be on the device, and then there'll be some levels at which even within the device they cannot be exposed beyond a certain trusted partition and so forth. I think there's going to be these levels and risk versus protection kind of trade-off that everyone's going to have to understand. And depending on the prevalence of attacks, then the certain things will become more efficient or more protective. And so that's how I've seen these things continue to go.
Overall, we would imagine that the security protection mechanism will have to evolve, I guess, together with edge computing, and I guess the users would also have to be more and more better educated about the levels of security choices they have. Okay, so we still have a little bit of time. Is there any question from the audience? Please come up to the mic if you have any questions.
I have a somewhat vague question to ask. As we push more functionality to the edge, picking up on what Shin you just said, you're pushing some of the complexity of managing things like security onto that end user who may be ill-prepared for it. What's the larger implication in how the business model is evolving? Are we pushing more functions on people who are less prepared to deal with it? Is it making the whole system more vulnerable as a consequence?
How's the drone systems coming up? How are you managing?
So that's a good question. I'd say even more generic. I'll give you an even vaguer answer. It seems that the more the technology increases, technology is increasing in being deployed and utilized much quicker than people understand what's going on behind the scenes. So I would say, at least from my perspective, more generally, yeah, people are not going to be prepared for the security issues that they're about to face. Whether they care or not, that's maybe a different question. I think some people care very deeply and others don't care at all. But that's, I think, yeah, I don't know how you educate society as a whole about this coming next wave of technology and how pervasive it is likely to be.
Just to add to that, again, edge computing comes in different forms. You see certain things in like AI PC or phones, but enterprises are doing a lot of edge computing aspects of as well. And their ITs are actually, monitoring, governing. So there are some aspects that you can bank on. Those aspects are already there. And some of the newer use cases, things are going to evolve, So how do you protect? I mean, we in Intel, I'll tell you, we're doing some of the fleet management aspects of it, manageability aspects of it. The current generation manageability through BMCs of the world are not enough. So we're looking to how certain things, data transmission, data ownership, data residing in the platforms, every aspect has to be secured. So there are a lot more work is going on. But you can also piggyback on the enterprise AI side of it when those edges are in the enterprise land. So there are security aspects of it already built in.
A big one.
Yeah,
Sorry. I was going to say comment slightly related to security, but maybe not exactly. Is especially as the edge gets smarter and smarter and smarter, will be supply chain security as well. We work in drones. There's a lot of politics involved with Chinese and non-Chinese drones and so forth, and so there's, I imagine, you see it today. Preventing NVIDIA from shipping the latest chips to China and so forth, and vice versa, and Huawei and all of those situations. So I think the supply chain is only going to become more and more heavily scrutinized as it pertains to security. And what does that mean? Whether it's security, information security, or just being able to procure the technology so that it remains pervasive and available.
Yeah. No, I think it's a good question. I do agree it's vague, and there are different angles to understanding what security means. But then when you follow it up and you asked about we're putting it in the face of consumers, then it feels more like it's not necessarily protecting IP, but it's more about thinking the development impacts of applications going faster than we're ready for. And that's the kind of question. It's interesting, but it's also interesting to understand, is edge any more sensitive than just the fact that development is happening at such a fast pace, even in the cloud, even with APIs that are enabled behind the cloud, and applications can reach out to any user regardless of if they're connected or not. And then at what level is that really what you're worried about versus things that are more specific? In fact, you might look and see a small model or a smaller form factor is kind of maybe less damaging because there's less it can do. It's a long debate even behind that. So security is a big question, and there's like adversarial robustness too, is the completely opposite side of what happens with all these things, but it's certainly an important thing to think about. And I think things do move kind of fast. That it's good to stop and ask those kind of questions.
Great. We are running out of time. Let's thank all the panelists for their insights.
Thank you.
And we will have Joseph to present his insights on the Gen AI for devices, on devices.
All right. Okay, so the second time I see it here, so I think we're all, thank you very much for sitting through the setup from before. All right. It might be my karma. Because I'm now on the official computer of the podium. Yeah. All right, great. All right, thank you very much. Thanks, everyone up there. Okay, so a lot of this I did talk about in piecemeal with gestures and things, but now I get to kind of illustrate some of the thoughts behind it. As I mentioned, one of the earlier comments, just understanding what is the compute needed to cover generative AI, how are we evolving, how do we make things better for generative AI to run on the edge. That's what I was going to focus on to kind of set the stage for the panel, and that's what I'll do at this moment today. There are two places where I'll focus because they're more canonical, you could say. Image generation is led by a diffusion model, and that's broadly applicable, not just to images. And then also large language models, GPT. I think that's a lot of people are very familiar with that. On-device AI, because of the panel, I don't have to say this exhaustively. I think we all know the energy, the personalization, the security aspects. The trends, did want to at least say that it's pretty amazing that we're going from text to image to multimodal as quickly as we are. And I'll have a few of illustrations to help you understand how to interpret multimodal, because it is implicitly a purely end-to-end type of thing, not that we're taking text and generating images or taking images and generating captions, but it's really a fundamental deep learning thing happening. This is a kind of a plot that I use a lot for our team put it together, AI Research, maybe a couple of years ago or so. What they did was they noticed what was happening in research, and then they started flagging things like certain areas that were very, let's say, hard to crack in domains suddenly were becoming solved, and behind it there were large language models, generative AI behind solving programming, mathematical reasoning, combinatorial optimization. Not necessarily the state of the art, but they were getting to a point where we still have to pay very close attention to this. And even more so, the model sizes at which they were addressing these problems fit squarely in devices that a lot of us have today. So if let's say we have a 10 billion parameter model, if you do like a 4-bit quantization of those parameters, that can bring you into the DRAM of your device or the storage, well within the storage capabilities of the device that's in your hand or the laptop that you work with. So just the fact that people were able to come back to these fields that were tough, that were blocked by data, blocked by different techniques, they just put in pre-trained models and built on top of that, that really opened things up. And we're continuing to see this transfer of ideas that we saw 2-3 years ago now becoming more in the line of product these days. We have had some great success with bringing these to our platforms. I should say that not just AI Research, but in concert with a lot of folks at Qualcomm. We had 8 Gen 3 mobile platform silicon. We had X Elite, which is the Copilot plus PC platform. It's really amazing that, let's say, GPT-4 came out late 2022, and now you have in your hands many different device form factors that have essentially the same technology now running locally on your device. And there's a incredible team behind this also at Qualcomm. But I should say the industry itself, the ecosystem, the research areas, the progress at which they've done these things has also been almost nerve-wracking. The rate at which models come out, the rate at which new capabilities have been coming out the past year and a half has really enabled these kinds of things to happen. Now, so let me talk about this idea of diffusion. So just to remind people of this picture, you were going to generate an image from a text prompt. This is something now that can be done in a matter of less than a second. And what's happening is a model goes through lots of data observations of noise to essentially degrading an image, and then it can learn to denoise that. And through the process of the way that people train it and condition on it, on the training, they can generate images from this denoising process. And at the heart of it is this UNet. It's a 860 million parameter model that is denoising this to produce a latent that then becomes a very fine pixel, high detail pixel image. This UNet is kind of the bottleneck in the compute because it's being run so many times. It's the biggest part of the network. It's very compute intensive. And when we look at this and we look at all the applications around diffusion and denoising, not just generating an image from text, but improving an image or even going into trajectory planning, it's interesting, like if we can make this diffusion process run effectively on the edge, then we can do things like robotic trajectory planning. So what the team ends up doing is they look at different parts of how the network is run and see what can we do to distill the model into something more efficient. And interestingly enough, not necessarily something smaller, just something that's more efficient. So, and you may define it like there are certain operations in silicon or in the software stack that are slower because they have maybe more multiplications in them. And we might want to replace that with convolution or something that's more, it's like a better way of sharing weights or implementing them. And then we change the network. That's already a big step forward. Then we can look at different conditioning of the model and then distilling the model to do the same task, but then do it faster, so to speak. So the original stable diffusion model, for instance, it would render an image in 20 iterations. And then if you took longer, it would be even nicer. We can take the same model and then use the original 20 iteration model as a teacher and then teach a new model basically to do the same task in 2 iterations or 4 iterations. And then that's a dramatic saving that gets us under a second. And these are the kinds of things that allow us not necessarily to make the model smaller, but the provision of the models into the task that they're trying to do, targets that better. And so this is how we get sub-second. Depending on how you train it, there might be a small loss in accuracy. That might be what you want. Or it might be more important that you want the latency for the accuracy. Or if you spend more time training it, you might be able to get where you're at and with the original model. A lot of that is part of the machine learning aspect of the design, and then you put that in with the end-to-end software hardware optimization. So that's one canonical piece of generative AI. Another important one is just looking at AI assistants. And so we had this demonstration of running an AI assistant on a phone.
In New York, departing on December 1st.
Thank you for that sound.
Here is the travel plan for your destination.
Can you add 2 adults to that plan?
Here is the modified plan.
Can you change the departure date to December 15th?
Here is the modified plan.
Okay, submit that.
Okay, I will send your plan to the travel website. Here are your booking options.
So I wanted to kind of sit through this demonstration so I can highlight a few important points of the language model as it's running. The first thing you notice is that the voice is driving a lot of the interaction. There's like a ASR and a TTS, of course, there. One interesting thing, though, is we're understanding when the speech itself is directed towards a task and classifying that towards a specific task of filling out a web form into a travel planner. And so from that standpoint, we have to have a model that's capable, or there's a context for that particular task in the model, such that it form fills to that web page. And in addition, you may think that we need to just generate tokens fast enough for us to read it or fast enough to render the speech as you're hearing it. But when you're doing applications like this, it has to run a bit faster because form filling out the web and understanding the situation at which you have to take what was spoken and figure out what needs to be sent, that generates a lot more tokens behind the scenes. And we want this process to be interactive, so we can't leave the user waiting too long for that. So there's going to be really a need to try to optimize this as much as we can. And so, at the heart of this is a transformer model, a large language model that amazingly, it's just trained on a huge text corpus to predict what's the next word in the corpus that it gets. And that's essentially what it does. And as a byproduct of that, when we use it, it generates one word at a time. And so you run a huge model just to generate the next word, and then you take that word, and then you generate the next word after that. And then you can imagine that if we have 7 billion parameters that will not fit on a chip, we have to always run back and forth between the DRAM. This kind of a process is very bandwidth limited. So our ability to speak fast to and from the user really comes down to how fast can we generate tokens? Do we have to always move the model each time just to generate the next token? And so the team looks at this. Here's an illustration of this. I forgot that this is illustrated, but here you can see that the original prompt that's sitting there. After that, we have to go and generate a word at a time, and each word requires running through all the model parameters at that time. So there are different ways to solve this problem. Trying to make the model smaller at the onset is immediately important. But one interesting optimization you can do also is have a smaller model do drafting for the larger model. So interestingly enough, small models, they may not have the reasoning capability, but they will master grammar fairly well in the target language. And maybe all you need to do is just complete a thought, or you can have, so in that sense, what happens is we have a small model, in this case, about 15 times smaller than a target model, generating 4 tokens at a time. And then the large model comes in, checks it, and then maybe accepts on average 2 tokens at a time. So then every time now we call the big model, we get 2 tokens instead of 1. That's like double the ability, double the token rate that we get within the same constraints of the memory and the same DDR bandwidth and so forth. And these are the kinds of games that we try to play to optimize the system once we understand more of what's happening within the network. And there's different ways that you can speculate. There's different ways that you can verify, and that's a fruitful area of research and innovation still. But this is what we did last year to show that we can be able to get token rate fast enough to be able to address these AI assistant type of use cases. Now, the other interesting thing that I alluded to was during the panel is that we can start asking questions about pictures, and just by taking a picture, encoding it, and then it becomes embeddings and tokens that are going into the original large language model with some alignment that we do between these. Now, what's amazing here is that we're not starting over and retraining a new model or retraining even a new architecture. We're actually reusing a lot of things that were pre-trained just in the text-only paradigm, just in the vision-only paradigm. And that allows us to carry over all the things that we did for optimizing these networks just to text-only and carry it over and do text plus vision. And so this is something we did earlier in February at MWC, where this was a very popular open source language multimodal model where you could take a picture and then ask a bunch of questions about it. And we were able to demonstrate that with the same techniques we had last year, we could onboard this kind of a model and bring it together. And then from an application standpoint, this is really a fascinating one where there are other examples like this, but there's one that I particularly like where you ask a question about a dish and you say, how many calories are in this dish? And it will break down, I see this kind of ingredient, I see this many of this ingredient, and reason as to how many calories are there. And it's not necessarily that was part of the training corpus. It was just that's how much foundational knowledge is in these models. And it's just a matter of fine tuning them in the direction that you want them to be good at. And then so we see this kind of ability. The company is moving as fast as we can to bring these to a lot of people to develop. What we showed, we're bringing into with the AI hub, the Qualcomm AI hub, to be able to let folks try these things out. You can go visit this website. It's a way to also bring your own models and then deploy them on our silicon. There's more and more evolution of the tools that are happening there. And then I'll kind of leave it there just to give you a sense again of what's happening at the edge and how compute is evolving to bring generative AI there. Yeah, thank you, everyone.